middle. So let's say you have scores ranging from 0 to 100, right? That's maximum score you can get is 100, minimum is 0. Now, for any exam or for any assessments that you give those students, the normal distribution, the theory of the whole normal distribution expects that, let's say from, you'd have, let's say, there's actually a percentage for this. There's actually a ratio for this. I can't remember it right now. So the numbers I'm going to call now are most likely not accurate. Don't take it to the bank. Do not quote me. So let's just spitball. So the normal distribution theory would tell you that something like 10 or 15% of students would likely get between 0 to 20. Let's use that as our very low scores. And then another 10–15% would get between 80 and 100. So very high performance and very low performance would be little percentages. So let's say together it's about 30% of the class, while the remaining 70 would make up the majority of the middle, right? So from 21 to 79, most of the class would fall in there, average students, right? That's the whole normal distribution thing. So when you plot this, the distribution on a 2D graph ends up giving you a curve that looks something like a bell. That's called the normal distribution curve. So all of this story that I'm telling you is just to let you know that normalization tries to make your data into a normal distribution. That's what it does. Tries to make it fit into that bell curve. At the end of the day, all of them are affecting your skill and how the data is distributed, right? The difference between each of these things is how they affect the scale. Okay. So while let's say something like your min-max scalar would shrink the data in each feature to come down between 0 and 1. That's what it does. Min-max is trying to rescale everything to fit in between 0 and 1. Your normalizer is trying to make the data become like have a normal distribution and look like a bell curve when it's plotted. So to do that, to transform that data so it has a mean of 0 and a standard deviation of 1, right? That's what it does. So by the time I think the math behind it is it finds the mean of that particular feature, then it subtracts the mean from each of those entries, and then it does some other division or something like that. So let's say you have 2, 3, 4, 5, 6 as the entries for one feature. It finds the mean. So let's say your mean is 4. So for each entry, it subtracts that mean. So 2 minus 4, that becomes minus 2. This minus 4, that becomes minus 1. It does all of that, and then does some extra something to make sure that the standard deviation for the whole thing is 1. So yeah, I hope I was able to clear that up for you. They all affect the scale, they all affect the distribution, but the difference is just how they affect it and what they try to achieve, right? So like I mentioned when we handled pre-processing the first and second time, most depending on what you're working on and your knowledge of the data, like your what's it called, subject matter expertise, and also your knowledge of the models and the way each of these scalars and normalizers work. Those are the things that would influence what you pick. Most times we use standard scalar. I believe it's the most popular. Personal opinion, not financial advice. I believe it's the most popular. That is standard scalar. But then, depending, you might find yourself working on, let's say, data for like medical research, and it's very niche, and you need the data to have these specific characteristics for the data you're working with and for the model you're going to be training. So you look for the tool that is going to give you that kind of transformation and that kind of effect on your skill. Okay? Did that answer your question?
Yeah, thank you so much.
Sure thing.
I have also very few questions. I don't know if I can ask.
Go ahead, go ahead.
Okay, so my next question is that when do we know to uh to reduce the dimension of our data sets to perform like PCA as an example?
Sorry, did you say how do we know when to reduce the dimension of our data set?
Yeah, exactly.
Okay. By dimension, you mean the number of features, right? Just to confirm that we're on the same page.
Yeah, the number of basically the
All
number
right,
of the
cool.
sets.
Okay, okay. There are a bunch of things to consider. First of all, the data. And like you can pick up a data set and you're seeing 200 million features. You already know right off the bat that that is most likely too many features. So you should already be thinking, I should check if it's possible to reduce the dimension, right? Um, so that's one thing that you can consider to decide whether or not to reduce dimensions. Then other things would most likely come up with exploring the data and analyzing it, right? For example, if you have a bunch of collinearity between features, then you don't need a bunch of those features, especially if you have a lot of features. If you have just 6, 7, 8, 9, 10 features and the collinearity is not strong, right? You don't have very strong correlation between the features. You could decide to let it go and just see what happens. Maybe even play with it, try with all of them, try with some of them, stuff like that. But if you have a bunch of features, so it's case by case, basically. There's no hard and fast rule that says whenever you see this and this, you must reduce your dimensions. It's case by case. You consider how many features you have. You consider um, uh, correlation and collinearity. You consider how much variance is described by each of those features, right? If the variance is little, it may not contain so much information for what you need, right? You consider the time it's going to take to train your model on such a huge data set, because more features means larger data set. You consider the computational costs if you're doing this in production. It's not just something that you're doing on your local device to test one or two things out. Then you could also consider after training, right? Um, I want to get this right. When you have too many features, it can affect your what's it called? Bias variance balance, right? I think having too many features, yes, it can cause your model to overfit because you're giving it way too much information, and a bunch of those things could be noise, right? So by the time you're done training your model and you check the performance, let's say you didn't have too many features. Let's say you had like 10, 11, 20 features, and you felt it's not too much, let me work with it. Then you train your model and you're not impressed by the performance. And you actually realize that it's overfitting. You check train score, you check test score, and realize that it's overfitting. You could also consider reducing the number of features. That is one way to try to, shift that balance between bias and variance. So yeah, it's case by case. There are a bunch of things you consider and decide. There are a bunch of things you consider before deciding whether or not to reduce your dimensions. Did that answer your question?
Yeah. So, what is the goal of a dimension reductions? Is it to like reduce the size of our data set? What is the goal?
That's one reason to reduce dimensions, to reduce the size of the data set. It's not the primary reason. The primary reason is to ensure that we have the most meaningful subset of our data to work with. Like I said, too many features unnecessary. It will introduce problems for. It's like you're a student in school and you have a bunch of. Okay, let's say you're a student in school. Yeah, that would be a good example. You're a student, you just got into the university or into a secondary school, and there are no teachers, and you just know all the possible courses or subjects that you could be tested on in the standardized examinations. You know that there's math, there's English, there's geography, there's physics, chemistry, biology, there's literature, there's arts and crafts, all of those things. And you're just given access to a library full of resources for all of those things. It's too much information. You're going to overwork yourself trying to cover everything because you don't know what you should focus on, right? You're going to absorb information that you most likely wouldn't need because with a structure and with teachers and with a system, you know, okay, I'm going into the sciences. I don't need to bother myself so much about literature and arts and crafts and maybe economics, right? I focus on my core sciences, physics, chemistry, biology, math, further maths, you know, stuff like that. So it's the same way. If you have too many features, you're giving your model more than it needs to work. And as much as we say that data is very important, too much data, or rather unnecessary data, is problematic, right? Because if you have features in there, you have data in there that is not particularly useful for what you're trying to predict or what solution you're going for, that feature becomes noise. It might be an important data piece generally to the company, to the field, right? It might even be an important feature or data piece for a different problem, right? But for this particular problem, if it doesn't contribute as much information, it doesn't really help you figure out what you need to figure out, it becomes noise. It becomes something that gives undue influence. So reducing our dimensions is primarily to, you know, sieve the data and remove the chaff and be left with meaningful features that actually transfer information to the model that you can actually learn from. Not just giving it everything and telling it to figure it out, right? That's our primary reason for dimension reduction or dimensionality reduction. Then there's the reducing the size of the data sets because, you know, the larger it is, the more time it's going to take your model to go through it. Then there's the computational cost as well that comes with having so much data and so much to run your model and your iterations and your inferences on, right? So yeah, all of those are reasons why you would reduce your dimensionality.
Oh, okay, okay, I understand. Thank you so much. And my last question, which is these non-negative matrix uh, factorizations. So I build a recommendations model that kind of recommend articles. I try to build that from scratch. So I was really impressed by the result I get. So my question here is that does recommendation system use the same uh, architectures of non, or in other words, can I use NMF to build a recommendation system like for a movie or for a music industries? So I wanted to understand this.
You want to know if you can use NMF in the music or movie industries? Is that your question?
Yeah, because I built a recommendation model, article recommendation model. and I test it. It performed pretty well. So I wanted to know if I can apply the same principles like to videos or music to kind of recommend videos to people, or uh, like music to people, just like YouTube perform.
Yeah, recommendation. Yeah. Okay. First of all, amazing stuff. Color me impressed and color me I don't know what other word to use in there, but amazing stuff. Big ups. Secondly, the simple answer to that question is yes. One of the NMF is, you already know, it's whenever you talk about recommendation and stuff like that, we start thinking about unsupervised learning. So NMF is an unsupervised learning algorithm, and it's usually used for like high dimensional data and stuff. I don't know in depth about NMF, honestly, but yeah, generally, it's applied uh, in stuff like image analysis. Lots of features to work with, and stuff like text mining and recommendation systems. So yeah, that's one of the applications for NMF. So yeah, you can use NMF for stuff like music recommendations and movie recommendations. It can be used in there, right?
Sure. Thank you so much. That's my all questions. Thank you so
All
much.
right. All right. Yeah, thank you for those interesting questions. It made for a good conversation. Okay, does anybody else have questions, or should we go right into the project? Any other questions? All right, then let's get into it. We are 7 on this call. That is sad. It saddens me. I am almost moved to tears. I want to cry. Oh well. Let's get into it. If you see any of our fellow cohort mates, let them know that they made me cry, or they almost made me cry today, and I shall hold it against them. There are scores to settle. Let me share my screen. What the hell is that? I think it's this. Hey, can we all see this? Can you see my dancing mouse? I'm on the tab, so I can't see any reactions if you guys are reacting. So please, when I ask questions, just unmute your mic and respond, okay? So I don't have to be switching between tabs. So can we see this? Did you say no?
Yes.
Yes. Okay. All right, let's begin. So, okay, before we begin, was everybody able to finish the projects? Okay, let me ask a more direct question. Who was not able to finish the project? Who has not been able to, because you still have some time to finish it? Okay, I'm going to take that as everyone has finished it. Did anyone run into any problems?
I actually I actually haven't finished the project.
Okay, have you started? Did you get stuck somewhere, or it's just time?
It's just time.
All right, cool. Is there anyone that's run into any bottlenecks or hiccups? while doing the project? Anybody? All right, then, in that case, this should be a short and quick one. We'll just breeze through it. You guys just interact with me. Let's get this party started. Okay, so a dental rental company needs your help, yada, yada, yada. The company wants you to try out some regression models which will help predict the number of days a customer will rent a DVD for. So you already know that we're dealing with regression. What just happened? Oh, sorry. So we already know we're dealing with regression here. And the company wants a model which yields a mean squared error of 3 or less on a test set. So we have a target MSE here. This is your success metric. Is it 3 or less? Is it less than or equal to 3? That's the MSE. The model you make will help the company become more efficient in inventory planning. All right, and our data is provided here. These are the features we have: rental days, return dates, amount to, rental rate to, etc. And all of these. And we have some instructions here, what to do and how to determine success. So that's why I'm opening it in the project interface today, so that we can go with the instructions. All right, first things first, we need to import our modules, import our dependencies. We have pandas, numpy, twin test splits, mean squared error from metrics, standard scalar, seaborn, and pyplot from matplotlib. Does anyone not know what any of these things are or what any of these things are used for? Anybody? Anyone? All right, cool. So yes, we import all of these. Let's run this tab to make sure it's imported. There's several other. And okay, we've been told to read in the CSV file. I mean, we have to do that. So let's read this in as rental DF. That's the rental data frame. That's our first instruction. And it says create product named rental length days using the column rental date and return date and rental date and add it to the pandas data frame. This column should contain information on how many days a DVD has been rented by a customer. All right, so good thing about these projects is that they introduce us to some new things, right? But before we go about doing all of that, we should explore our data, right? Wait, what did I just do? Sorry. I said explore data and I clicked explore data. So we should first do EDA in it. Okay, and you can unmute your mics, guys. Let's just talk and run through it. So first thing we want to do is check the head in it. Why am I saying that? Rental df dot head. Right. So we have a feel, we get a feel for what we're working with. So we have rental date that looks like this. This is dates and time and some extra jar. Then we have return dates, amount, release year, rental rates, length, replacement costs, special features. This is a peculiar one. Then we have all of these ratings, NC13, NC17, PG, PG13, R. Basically, what is the movie rated? Amount to, length to, rental rate to. Okay. So we're told that the DVD company wants us to predict the number of days a customer will rent a DVD from. Now we do not have the number of days in their data sets. So the data they're providing us with does not have that particular column or label to begin with. So we're going to do some feature engineering there. Okay, is there any other thing you want to do for EDA? Just unmute your mic and speak or suggest any other thing you want to do for your exploratory data analysis. Okay, let's look at rental DF. Let's look at info. Boilerplate. Okay, so info lets us know that there's no empty cell for all of the features. And it tells us the data types we have. Rental date and return date are both objects. So our DF is storing these as just regular text or string, right? So they're objects here. Then the rest of them, we have a bunch of floats. We have one more object that's special features. We can see why. And then the rest of them are integers, and these other three are floats. And lets us know the kind of data we're working with, right? We could also do describe, right? So you can do rental yes, describe. Okay, and then we can look at the statistical summary. We can see the differences here, the mean changes here. Obviously, the mean for a month and the mean for a year is not going to be the same, right? The year here is between 2004 and 2010, and the mean is 2006. This, you don't really need mean for year. We have the range and what is at the various percentiles. Then here the mean is 4.2, that's the mean amount. Minimum is 99. I'm assuming this is in dollars, so let's say 99 cents. And the max is $11.99. The rental rate is between 99 cents and $4.99. Length is from 46 to 185. I'm guessing minutes. Replacement cost is from $9.99 to $29.99. So basically, we can see that the spread for a lot of these things is different. This is from 0.98 to 143. So that's quite different from this one. It's quite different from this amount. Then length, here we have from 2,916 to 34,000. So that is also quite different from what we have here. And rental rate to this from 98 to 24.9. Where is that? Yep, it's also different. So the spread is different across. So if we're working with models that are affected by scale, we would have to do some centering and scaling for this data. Okay. Any other thing that I want to do for EDA, or is that quite enough? All right, so let's move on to the instruction that was given. Let's call this, what shall we call it? Let's call it feature engineering. What just happened? Okay, we're about to engineer a feature. So instruction says, create a column named rental length days using these two columns and add it to the pandas data frame. So that means we want to have our pandas data frame is rental DF, and then we want to add a new column into it called rental length days, right? So this is what we're trying to add. How do you go about that now? Now it says we should use the columns return date and rental date. So simply, we know that the number of days that the DVD was rented for by a particular customer would be the difference between, would be the number of days between the day they rented it and the day they returned it. So if they rented it on the 2nd and returned it on the 4th, then it was rented for 2 days, right? So we need to do that math. We need to do return date minus rental date. Our problem now is that both of these are in the data type object, so we can't perform that kind of operation on them, right? So what we do for stuff like this is we convert it to datetime. We convert both of them to datetime, then we can perform that operation, right? So we call rental df. Let's start with rental date. Rental dates, and then let's replace rental dates within our data frame with, let's call pd dot to date time. Did you guys come across this while you're working on this project? If not, I'm interested to know how you went about this particular instruction. Did you?
We came across it.
All right, beautiful. Okay, so we're saying go into the data frame, our rental data frame, and replace the rental date with rental date, but in date time type. We want to change the data type to date time. Okay, then let's do the same thing for return date. Good. So we have rental date changing to daytime and return date changing to daytime. Now we can perform a mathematical operation on it. So we call that rental length days would be return dates right, minus rental dates. All right. Now, when we convert this to date time, where is our example? Let's look at the head. So when we convert this to date time, we're going to have year, month, day, hour, minute, second, and milliseconds. We're going to have all of that information. So if you subtract one of these, let's say you subtract this from this, it's going to give you how many years, how many days, how many months, how many hours, how many minutes, seconds, and nanoseconds in between, right? But we only, for this particular purpose, we only need the days, we need the length in just days. So we want to, so the response that we're getting, we just want it to come in days. So that's what we're going to do. Run this. Rental date, where's that? Where's rental date? Rental date, DT. What is our problem here?
You use rental
dates on the variable name. The DF instead of rental DF.
Okay, rental DF. Thank you very much. That would have taken me forever to see. All right, beautiful. Okay, and let's see what it looks like. So let's call rental DF dot head. Okay, so first of all, you can see that this has changed. The representation here has changed from what we had up here. Where is it? It's changed from this to date time. Actually, we have this T in between to let you know that this is where the time begins. And then the plus yada 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 that we had at the end is now 8.000. So you know that those are milliseconds. Then at the end of it, we should have, yep, our number of days. So we know that this person held onto the movie for 3 days, 2 days, 7 days, etc. This brings back memories. There used to be a time where you could go to a shop and rent a movie and hold on to it for some days, see it and return it and rent another one. Fun times. Okay, so we've satisfied this, right? Satisfied this part. Next says create 2 columns of dummy variables from special features which takes the value of 1 when the value is deleted scenes, stored as a column, deleted scenes. Okay, and then the value is behind the scenes, stored as a column behind the scenes. So from special features. Let's see the recent head. Where's that? Okay, so this is special features. So basically, we want to create 2 new columns, deleted scenes and behind the scenes. And we want deleted scenes to have a value of 1 for any entry where the column special features contains deleted scenes. And then we want the column behind the scenes to contain 1 for any entry that contains behind the scenes, and the rest will be 0, obviously. So for the column behind the scenes, this would be 1, 1, 1, 1, 1, while for the column deleted scenes, these particular entries would be 0, 0, 0, 0, 0. That's what we want to achieve at the end of the day. All right, let's get into it. So this is another new thing that this would bring to you. So this is another way of, this is a specific way of creating dummy variables instead of the generic encoders, right? So in rental DF, we want to create a new column deleted scenes. Scenes. And this is going to be, we're going to use the numpy.where here. So this is the mp.where. Now we're saying wherever special features contains this string, wherever it contains deleted strings, right? For every row that contains deleted scenes in that column, store it as 1, otherwise 0. Then we do the same thing for this is behind the scenes. Behind the scenes, and this would be behind the scenes, right? Everything good. Let me put one line in between here so I know. Rental DF, deleted scenes, and be aware, rental DF special features, and that it contains a string deleted scenes, basically 1, and then behind the scenes where it contains, yeah, I think that should be good. There are other ways to do this as well. I think let's run this first and confirm that it works before we start adding anything extra. Let's call rental df.head to confirm that it works before we start seeing a bunch of red. Beautiful. 2 things that make you happy: no errors and new errors. No errors is the best. If you get an error and you do something and you get a new error, that is also progress. Okay, so like I said, for these ones that we can see up here, there will be 1 for behind the scenes and 0 for deleted scenes, and it tracks, right? So I was saying that there are some other ways to do this. I'm just going to add this other one as a comment, so we don't ruin what we have already. So you could say, let's copy this. Let's say rental DF deleted scenes will be equal to rental DF special features string that contains deleted scenes as type int. So here we're not even specifying put 1 or 0, because it's like it checks special features and it's basically like a true or false thing. Does it contain deleted scenes? And if it does, that means for that particular entry, it's true. And if you convert true to an integer, it stores as 1. So if it checks and it doesn't contain, that would be false. If you check it as an integer, it will store that as 0. So it gives you the same thing as this. So yeah, you can do the same thing. Just copy this and replace deleted scenes with behind the scenes, and the same here. Okay, let's trudge forward, ahead. So this has worked, and if you want, because from just the head, you can only see a bunch of zeros and ones, and it might seem pointless. Why? If it might feel like everything here is 0 and everything here is 1, so there's no point. So to be sure, we can revisit our old friend value counts to make sure that we don't just have a bunch of zeros on this whole column and a bunch of ones on this whole column, right? So let's call, which one should we call? Let's call deleted scenes. Deleted. Let's value and okay, so that tells us that it's almost split evenly. We have a bunch of zeros and a bunch of ones, so we're not wasting our time. We can do the same for behind the scenes. Yep, and a sizable split too. Okay. All right. Then the next instruction says, make a pandas data frame called X containing all the appropriate features you can use to run regression models. Avoid columns that leak data about the target. Okay. Now, what we are our target is rental length days. That's what we're trying to predict. So what columns would possibly leak data about that? What columns? I need you guys to give me responses for this one.
I think the column that we just created through feature engineering, like behind the scenes, deleted scenes, and the length of return, as in the return length date, rental length date, yeah.
Rental length days, okay.
Yeah.
Why do you think behind the scenes and deleted scenes would leak data?
No, I mean the data that we need.
Okay. I get you. So you're saying we need this, and this. These three.
Yeah.
Okay.
Yeah.
Remember that this is our target though, and what we're trying to create here is X. So we're looking for the features. So definitely we can't have rental length days as one of our features. Right?
Oh yeah, that's true. That's true, yeah.
Okay. So and I'm trying to find out, here they said avoid columns that leak data about the target. That's my focus for this question. This is our target. How many days the movies were rented for? 4. So from all of these things, which of them do you think can leak that data? Like if we have these columns in our X, it might already inform the model. It might give you some information about the days without us meaning to. Which of those do you think?
Then that's the
Obviously,
rental length.
yes, definitely. Obviously, you have to have rental end days first, because that is the target. If you have the target in the training data, what are you training for? So we have rental length days. What else?
That's all.
That's all. Okay. So remember that we got this, we didn't have rental length days when we started this, right? We engineered rental rent days from 2 features. Where is it? Where is it? Yeah. From rental date and from return date. So if we could perform this simple mathematical operation and get rental length days, you guys believe that it's possible that your model can, steal this information too from these features if it has them. So since we're trying to predict the days and you can get that from the dates, that is a possible avenue for leakage. You agree?
Yeah.
Beautiful. So let's drop them as well. Let's drop return dates, and let's drop rental. Good. So that's for leakage. Then generally, are there any other things you need to drop? We drop this, we're dropping this. We have these other ones. We should drop this because this is an object and we've engineered 2 features out of them being deleted scenes and behind the scenes. So let's drop that as well. Special features. Okay, are we good to go? Does anyone have anything else they think we should drop? All right then. So let's run this and see what we have now. What is the problem? Oh, columns. Sorry. There we go. Now we have all numeric and without any leakage. We don't have rental length days. Yep. We don't have rental date and return date any longer. So X is good to go. Then we should have our Y as well. So our Y is, hold on. Let's read the instruction too. Let's follow it like good students. Choose the rental length days as target column and save it as a pandas series. Okay. So where are we? Okay. The Y is okay, there we go. We've created our Y and we've created our X. Following the pre-processing, you need to split the data. All right, we know how to do that, right? So we have our X train and our X test. Then we have Y train, Y test would be train test plates of X and Y. Let's use, okay, yeah, They're given instructions here. Are any features that leak data about the target variable include 20% of total data in tests? So test size is 0.2. Then, okay, set random state to 9 whenever you use a function or method involving randomness. All right, then. So we're going to use random state 9. You guys know what random state does, yeah? We all know what random state does, yeah?
Yeah, we all know. I think just to make the data to be reused, to be retestable.
Yes, it fixes a state because this test, train test split is, it does a random shuffle. You know, if you've played cards, any kind of cards, it does some sort of shuffle and then it splits it. So random state tells it, gives it a seed, gives it a particular fixed number to always shuffle using that number. Right? It's like, I'm not saying that this is exactly how it works, but it's like always pick it 9999, share it in nines or something like that. It just gives it a C so that if you come back to this code in 200 years, or if you give someone else this data set and they use this same random state and do the exact same things you did without copying you, if you just tell them, I did this, I did that, use random state 9, they're going to get the exact same results. So it gives you reproducibility. Okay, so we've done that. And the next instruction says save the model. Okay. Recommend a model yielding a mean squared error less than 3 on the test set. Is a broad range. Any model that gives less than 3 on the test set is good. Save the model you would recommend as a variable named best model and save its MSE on the test set as best MSE. Now the interesting part. Okay, so when we did the describe earlier, we saw that there was quite some spread. So they don't tell us what model to use, so we're going to try a couple of them, see which is better. So since we would probably try some that are dependent on scale and distance, best practice, let's just scale it. So I believe we already have standard scalar up here. Yep, we have standard scalar here. So let's initialize. And we have the scalar is standard scalar. Then we create X-string scale. And we call that should be scalar.fit transform. Okay, so we're calling scalar.fit transform on X-train to give us X-train scaled. And we do the same thing for X-test. All right. Good, we're all scaled. Then the games begin. Okay, let's start from our trusty friends. We're doing regression, so linear regression, right? So
sorry, just a quick question.
Go ahead.
Okay, so if there's no need to scale, and then we still go ahead to scale, will it affect, or will it give it a negative impact?
No. Scaling doesn't have a negative impact. Okay. Which is why it's just best practice. If you might use, if you know for sure that you're going to use something that does not require that, you don't need to scale. If you do scale, no problem. If you don't, no problem. But if you end up using a linear or a scale or distance dependent model and you did not scale, problem.
Okay.
Let's call linear regression from, it should be taught. Mescaline the linear model, we call it linear regression. Now, we can't really tweak linear regression, so let's call the tweakable cousins. Have we met these? Have we met these models? Lasso and Ridge. Have we met Lasso and Ridge regression? Have you guys come across them in the course?
Yeah.
Okay, beautiful. That would have been quite some derailing. And we understand them, yeah? Or at least we have an idea of what's happening there. Do we? Does anyone not know what Lasso and Ridge regression are all about? So if I ask anybody, if I pick anybody on this call and I say, explain lasso regression to us, or explain ridge regression to us, you do it confidently. Because I'm about to call a name. Okay. I don't know whose voice I've been hearing. Has it been Isaac or has it been Franklin? Which one of you? It sounds like Isaac. Who has been talking with me?
It's Franklin.
All right. Okay. So you're off the hook for this question. I'm going to ask two people. Chima, can you tell us what lasso is all about? Just very briefly. Am I with us? No.
Oh, sorry. I thought I was speaking. I was muted.
All right, no problem. Go ahead.
Yeah. Okay. So you were asking the different. Is it the differences that you were asking?
No, just a brief explanation of lasso.
Okay, just the lasso. Okay.
Yes.
Lasso regression is just like okay. Let's say it kind of improves it gives a penalty to the loss function.
Okay.
Yeah, so it's more of a penalty. I don't know how to put it though, but
I like the word you used, penalty.
okay, so it's just like you set the coefficient to. There are some terms I'm not really familiar with, but I'm just using my head,
Yeah, that's
the
fine.
English in my head. Yeah. So it kinds of use coefficients. So big errors gives big penalty. Am I right on that? So.
Not totally. You're right on the penalty on the model, but what the penalty is going after is where you're missing it. But that's fine. We'll explain it. Let's see. Who else shall I call? Franklin, you're off the hook. Okay, Isaac, let's hear from you. Can you give us a brief explanation of ridge?
Okay. Can you guys hear me?
Yep, go ahead.
Okay, so like the last speaker said, more like a way of penalizing, like you said, but it's dealing with like the residual sum of squares in a way. So it's just like trying to reduce it, bring it down a bit.
Okay.
Yeah.
All right. Sorry, what did you say?
Like, am I right on that?
Yes, you're on the right track. I was going to ask would you be able to differentiate between lasso and ridge? They're very similar, and the difference is mostly mathematical. But would you roughly be able to differentiate them?
Lasso and reg.
Yes, ridge. These two. These two guys. It's fine if you can't. It's okay. I'm just asking.
Okay, let's say lasso is about. No, I don't think. I think what I want to say will not be right, so don't worry.
All right, no problem. That's fine. Okay, thank you guys. So lasso and ridge, these two, like I said, are cousins of linear regression, right? There are some it's linear regression with steroids or with some extra superpowers. And that extra superpower is regularization. So regularization is basically, like they said, it's adding some extra constraint or some extra penalty to our normal linear regression. So, sorry, you speak. Okay, Isaac, I think your mic is still on. Isaac, your mic is still unmuted. All right, so as I was saying, the extra superpower that these models attached to linear regression is regularization. Simply, what that means is what Isaac and Chima have told us. It attaches some penalty. So normally, linear regression works to find the linear relationship between your features and your targets, right? It finds some linear equation, and you know how the linear equations are. Y is equal to ax plus c. That's the very simple one. So the number of features you have gives you the number of x's. So it becomes y is equal to ax1 plus, if you have like 5 features, it becomes something like y equals ax1 plus bx2 plus cx3 plus dx4 plus ex5 plus f. F is your constant, is your y-intercept, you know, and all the x's represent each of your features, right? So you have the features already in your trained data set. You have the features, you have all the x's. You have the y as well because it's supervised learning. You have the features, you have the targets. What your model is trying to do is to find the A and the B and the C and the D, those coefficients, right? It's trying to find those coefficients that would, for every case, every set of features that you give it, with those fixed coefficients, it can tell you what the y is going to be. Those are your model parameters, okay? Now, while linear regression tries to find those parameters, it's doing something every time because of the what's the word? As it starts, just at the beginning, this model just guesses. It takes a bunch of random numbers. It will just guess, okay, A is 5, B is 0.2. It has no idea what they are. It just gives a bunch of numbers. Then it uses those numbers to make predictions on your training features. And it compares the predictions with what you actually have as your Y. And it checks the difference between the predictions and the actual, and that becomes your error, right? The error is in different ways, but for linear regression, I believe it uses the mean square error, right? So it checks the difference between predicted and actual, takes the square of the difference and sums it all up for every entry and takes the mean. So this is what's happening when you run your linear regression dot fit on X train, Y train. This is what is happening. It takes a bunch of guesses random parameters, uses those random parameters to predict on your X train. Then it compares those predictions with your Y train, and it checks the MSE, the mean squared error. So if it checks the MSE, it tries to adjust the parameters that it assumed in the beginning, and it keeps on comparing the MSE until it gets the lowest MSE it can get. So basically, your linear regression is trying to minimize the mean squared error. That's what's happening. Now, while trying to minimize mean squared error, it can have such large parameters. It can have A that goes up to 1,000 and B that goes up to 245 and all of that, right? And if you're not careful, this can end up overfitting. It can end up, trying too hard to minimize the mean squared error. And the more it tries to minimize the mean squared error, it means it's trying to fit very tightly to your training set. You get, because, okay, let me see. I hope I feel like I'm derailing a lot, but sometimes it's important to understand what is happening under the hood. Okay, let me try to open a whiteboard, see if that works. Let me stop sharing my screen. Can you guys see the whiteboard? Can you see the whiteboard?
I can't see anything.
You can't see anything?
No.
Oh.
Not yet.
Interesting. How do I share this? I would expect that this would be presenting.
I think he's saying that we should install an add-on for it.
Okay, you have to install it to see it. That's let me just share my screen so you can see what is on my own screen. My screen is very cluttered though. What just happened? Okay, let me just share this particular. Let me share this window. Now it's small. This is just annoying. Nope, this is not working. Okay, it's quite small, but let's just manage that. Okay, so this is what I'm trying to explain. So let's say this is a graph that we're working with, right? And this is where you have your X, and this is where you have your Y. This is sad. So these are X, and this is our Y, right? And then we have a bunch of points. Let's just say these are our points. These are data points. So for every value of X, there's a corresponding value of Y. And you can see that there is some sort of linear relationship. So when you start running your .fit, like I said at first, your model is going to guess values of parameters. And those values of parameters would give it like some line of best fits, right? So the line may end up being here. Okay. So it's saying, hold on. Let's say the line is here, right? Let me extend it this way. Stop now is okay. Okay, so let's say this is our line. So now, say we want to predict a value of a value where X is this. This is our value of X here. Can I change the color of this? Doesn't seem like I can. let's say X is here. Now for what the model has guessed, when X is this value, Y is 0, right? But from the data sets we have, when X is this value, Y is this, right? Because we have a data point right there that proves it. When X is, let's say this is 1, let's say this is 1 here. When X is 1, Y is, say, 1. When X is 1.5, Y is like 1.2. But according to our model, when X is 1.5, Y is like 0.1. So that is the difference between our predicted and our actual. So for this value of X, our predicted is 0, but our actual is 1. So predicted minus actual will give us that the error here is -1. If you square that, that gives us -1 times -1, that is 1. So we do that for each of these data points, and then we find the mean error. That is MSE. That's exactly how MSE works. So when your model calculates the MSE, it says, okay, let's adjust the values of the parameters that were guessed. So it adjusts the values, and then the line ideally would now come closer to where this is. So now the error is smaller, right? Then it does the same thing, finds the MSE again. It adjusts. This is what happens when you run .fit and it's loading and loading. This is what's happening. So it finds the error again. It adjusts the what's it called? The parameters. And let's say it now comes up with a line like this, right? Because it's trying to minimize mean squared error. So the more it does this, there starts to be a tendency that it's going to try too hard to be very close to each of these data points. And that is where you start having overfitting. It starts fitting to everything, even those that are, that have noise or that may be outliers and stuff like that. That is in the case where you didn't standardize your data set and all of that. So now okay, I think that is okay. I think we've got some what we need from that. So what regularization does is that it adds an extra constraint to the conditions that your linear regression is working with. At first, the condition is just minimize mean squared error. But then it adds the extra constraint and it says, as you're minimizing mean squared error, also minimize something else. So for ridge regression, it tells it minimize the sum of the squares of the parameters that you're tweaking, right? So that means now while it's also checking mean squared error, it's also going to take the square of each of those parameters and take the sum and also be trying to reduce it. So it's now trying to get a model that is really good and also a model that the parameters are not too big. This helps that model to avoid overfitting. Okay. And Lasso is also doing regularization, but the difference is in how it is doing it, just like with all our scaling options. So for Ridge, it's minimizing the mean squared error along with the sum of squares of the parameters, while for Lasso is minimizing the mean squared error along with the sum of absolute values. So it's not taking the square of the parameters, it's just taking the absolute value. We know what absolute value is. So it's whether it's positive or negative, you're just concerned with the core number. If it's -2, the absolute value is 2. If it's negative something, the absolute value is the number itself without the sign. So it's trying to minimize the absolute value. So at the end of the day, the result is that with Lasso, both of them are regularizing, but with Lasso, since it's trying to reduce the absolute value, it means that the parameters are going to tend towards 0. Like if that parameter is not very effective in the model, it doesn't give a lot of information, it's going to tend towards 0. So the least effective and those that have very little information to give might end up being 0 and just falling off. And then those features, it basically does some sort of feature selection for you and drops off some features, right? It's not like it's going to delete the features from your data set, but it will end up not using those features when it is trying to predict the Y. That's for Lasso. So it can end up giving you more sparse models in the sense that it can kick some features out of the equation because the absolute value is tending towards 0. While for ridge regression, it gives you, it doesn't give you more sparse ones. It gives you, what's the word? What's the word? I can't remember. Anyway, because ridge is taking the squares of those parameters, is not pushing the absolute value to the minimum. It's pushing the square of the absolute value to a minimum. It means that for something that Lasso might push to 0 and kick that feature off, Ridge might push it to 0.000000000 something. Because by the time you take the square of 0.0000009, it becomes even smaller and almost 0. It becomes 0.00000, basically double of the zeros, double of decimal points, and is much closer to 0. So Lasso is sort of a little harsher on the features that don't contribute a lot. I feel like I've talked too much about that, but did you guys understand the whole Lasso, Ridge, and regularization thing?
Yes, thank you.
All right, cool. Let's go back to... Yeah, go ahead.
Just a remark, there is also a model that combines both Lasso and Ridge. It's called
really?
Elastic Net. Yes.
Oh, yes.
Elastic Net. So it combines both L1 and L2 regularization.
Yeah, beautiful stuff. Oh, yes. You just reminded me. So, guys, the regularization that Lasso does, remember that for Lasso, it's minimizing the sum of absolute values of parameters. That is L1 regularization. L as in lion, L1 regularization. Then minimizing the sum of squares of the parameters, that is L2. So that's what Ridge does. So if you see L2 regularization for regression, you know that's Ridge. If you see L1, Lasso. Okay, thank you, Ismail, for that. Thank you very much for that nugget of information. Now let us proceed. So, like I said, linear regression is not exactly something we can tweak. It doesn't have hyperparameters that we can play around with. So it's just our base model. It is what it is. Lasso and Ridge, on the other hand, have those hyperparameters for how strong you want regularization to be that can affect the output of the linear regression, right? So that's why we're using sorry, let me share my screen. That's why we're pulling, you can see my screen, yeah?
Yeah, we can see your screen.
Okay, so that's why we're pulling linear, we're pulling Lasso, we're pulling Ridge. This is our base model. These are the ones we can tweak to see if we get something better than the base model. And they've already told us that we're trying to get MSE, so we just know the metric that's important for this project, which is the mean squared error, right? So we just import that mean squared error. Okay. Let's begin. So let's initialize our linear regression. Let's call it linreg. This is a cool name, linreg. And then call that linear regression. Then let's also call Lasso. So we know that, I think I'll just call linreg and Lasso in this cell. We'll just call Lasso here. And let's give it random states 9. Okay. Should we call? Let me just do this too, because let's go Ridge 2. actually. Let's go reach. And let that be reach. Random state lines. Okay. Then I'm going to fit each of them. Just going to play around with them and see what gives us the best. Our target is less than or equal to 3, so hopefully that's not too difficult to achieve. So we're going to fit this on our extreme scale and Y train. Then let's get our predictions. So let's call that Y pred lin. And now the in of predict on X test scaled. Right. And let us print the MSE. So let's use this. Linreg MSE is then it should be inside. That's a different type of formatted string. So this would be mean squared error. Mean squared error on Y test and Y pred lin, right? Print name like MSC, and I'll be mean squared error on Y test squared here. That should be that. Let's copy this. Then let's call lasso. Call this Y pred lasso, and we call lasso.predict. It needs to be lasso MSE. And this would be a Y pred lasso. So I have everything covered. Lasso the fits, extreme scaled, Y train, Y pred lasso, lasso that predicts, X test scaled, trains lasso MSE, is whether Y test Y pred lasso. That looks good. Then let's do the same for reach. Reach.fit, Y pred reach, that would be reach.predict, print reach MSE, is whether Y test Y pred reach. Okay, look good. Let's find out if it is good. All right, so linear regression has mean squared error of 2.944. Lasso has 5.95, range is 2.94. So on the base, without any tweaking, this is already less than 3. Both of these are already less than 3 without any tweaks. While this is failing. Now, so you are failing. Very sad. But since we have hyperparameters to tune, this could perform better. And, theoretically, these two could perform better. The base doesn't necessarily have to be the best. So let's go ahead and play around with it and figure it out. So let's call in some searches from SQ. And if at any point anyone is lost, just let me know. I'm just going through some of these things because we've gone over them a couple of times in previous classes. Grid search, right? Grid search CV. Let's also get randomized search. Can someone tell me the difference between grid search and randomized search? Do we know? Okay. Does anybody not know the difference between grid search and randomized search or random search?
I don't know the difference.
All right, but do you know what they do? Like, basically, do you know what these things are for?
Yes, I know what they're for.
All right, cool. So, okay, tell me what you know that they are for, then we'll differentiate them.
So basically, we use grid search CV to iterate through a number of models to get the one that fits best. Yeah.
Okay. So this step would be hyperparameter tuning. Let me finish this. Just give me a second. So let's set up the param grid. Let's just tune alpha. Alpha is the coefficient for that regularization. And that would be, let's take between 0.0001 and 1. And let's take 50. Okay. So this step would be hyperparameter tuning. In this case, in this particular one, I'm only tuning one hyperparameter, which is alpha, right? And I'm tuning through a list of numbers from, this is a comma, a list of numbers from 0.0001 and 1, 50 different numbers from 0.001 all the way to 1, right? And I'm trying to find out which is going to give me the best result, okay? Now, what grid search does is that for however many hyperparameters you have, it creates a grid of all possible combinations. So let's say I had another parameter here with, let's add another parameter. Let me call it the grid parameter. And the grid parameter is a list of 1, 2, 3, 4, and 5, right? So inside here, I have 50 different alphas. And here I have 5 grids. So that means for grid search, it's going to create a grid of all possible combinations. That means for each entry in grids, it's going to run it on all 50 alphas. Then if you pick the next one, run it on all 50 alphas. Pick the next one, you run it on all. You get, this would mean that your model, let's say, is rich. Please, you should remind me to remove this thing I put here when it's time to run, so that we don't start having a bunch of errors everywhere. So let's say our model is rich. This would mean that rich can take the arguments alpha equals something, and then grid equals something else, right? So that means for grid search, it's going to start is going to do alpha equals 0.0001. Really great. What just happened? Okay. So it's going to go alpha equals 0.0001, great equals 1. It's going to take this initialized model like this with these parameters, and it's going to run the train and do all the things that happen when you train the model. Try to minimize the MSE while applying this as the regularization constraint and all of that. It does that. It keeps the value. Then it's going to come and it's going to run the next value here. So I don't know what the next one is. It's supposed to be evenly spaced between this and this. So let's assume the next one is 0.20. It's going to run this, train it, keep the value of the mean squared error. Then it's going to come and pick the next one. Let's say it's 50. It's going to run it. It's going to come and pick the next one. Let's say it's 90 to run it. Is to do all of that, all 50 of them for grade equals 1. Then it will come again and change grade to 2 and start from the beginning and come and do alpha equals 001. It will run it, keep the value. Alpha equals 0020. It will run it, keep the value. So it's going to do that for every single combination, every possible combination in here. That's what grid search does. It goes through all of them and it tells you which gave it the best, depending on the scoring metric that you're using. Which gave it the best result, the best score. Randomized search, on the other hand, does not exhaustively go through every single thing. It goes through a certain number of iterations randomly. So if you tell it, okay, do 20 iterations. Okay, so here we have 50 possible alphas, and we have 5 possible alphas here. So that means the total number of iterations here is 250. That's 50 by 5. Because for each one, there's a 50, another one, another 50, another one, another 50. So 50 times 5, that's 250 possible combinations. Grid search is going to go through all of them. Now for randomized search, I could tell it, okay, just do 50 iterations. So instead of going through the 250 exhaustively, it picks 50 random possible combinations and runs the test and tells you the best out of the 50, right? So randomized search is by design not exhaustive. You tell it where you want it to stop and it does a random scan. While grid search is very meticulous. It goes through them one after the other with a fine-tooth comb, right? So obviously, this would be faster than this. The random search would be faster than the grid search, depending on your number of iterations. As long as the number of iterations does not equal, like for this, that the total is 250. As long as your random search iterations is not equal to 250, it's going to be faster than grid search because it has fewer combinations to search through. But so this is the pro for random search. It's faster, it takes less time, consumes less resources, less computing resources. But then for grid search, it's exhaustive. So you are absolutely sure that this is the best. Do you get me? You're absolutely sure that what it's giving you is the best you could possibly get for any possible combinations of the parameters that you have, right? So random search could pick 50 and scan through. It give the best out of the 50. The best out of the 50 may not be the best overall. May not be the best out of the 250 possible combinations. It just gives you the best out of a random 50 and you go with it. While grid search gives you the best out of all possible combinations. Yeah, so that's the difference. So in production, in real world scenarios where you have large data sets and time constraints and computational resource constraints and all of that, a lot of times you might end up using random search because it's not exhaustive. Okay? Did you get that explanation? Did it work for you?
Yes, very much. Thank you.
All right. Yes, where were we? Okay, so we have 50 of these. Yeah, I think we're only tuning alpha in this iteration. So let's call grid search. Oh, it's already 8 p.m. Well, we did start a little late. So let's call this on lasso. We've already created lasso, right? Yeah, we created lasso here. So you can just use that one here. Let's call this on lasso. Let's call on round grid. Then let's do 5-fold cross validation. We know what this means, right? So we know what 5-fold cross validation is.
Yes.
All right, beautiful. Machine learning engineers in the making. Lovely stuff. Then our scoring is neg mean squared error. Obviously, because we're looking for mean squared error, so we just use that as our scoring so that it's trying to maximize. Do we know? Okay. Do we know why this is negative mean squared error instead of mean squared error? Does anybody not know? Okay, so we all know. So we know what all of these things inside here are, even these n jobs. Does anybody not know? Go ahead and ask if you don't know. All right, that's good. I'm very happy. Please, if you don't know, don't hesitate to ask. Oh, that's why we're here. We are here to learn. Okay, so we're calling grid search. Estimator is lasso. Our param grid is this. 5-fold cross validation, scoring a negative mean squared error, and using all our processes. Okay, then we say grid search that fits on X train stable and Y train. Right, then let's just run this. It's not running. It shouldn't take so long, it's just 50. Yeah, that's done. What's going on here? Okay, so let us presumptuously call it best MSC. You can always rewrite that with a better one if you get a better one. And then it's going to be the negative of the best score, because we use negative mean squared error, but we want mean squared error. So we'll take the negative of the negative, which would be mean squared error. So that's going to be negative grade search dot best score. And then our best model presumptuously is going to be grid search dot best estimator. Okay, so let's print best MSE. Let's also print best model. See what the parameters are. Is all good? Best MSE is negative research, best score. Best model is research corresponding best estimator. Okay, let's see what that gives us. All right, and remember this was a grid search on lasso, and lasso gave us 5.95 originally. Now we're having 2.849, which is better than both the Bayes linear regression and the Bayes ridge regression, right? So that is good progress, right? And then our best model is giving us that alpha is 0.0001. We already set random state to 9. So that means the very first one was the best alpha. Okay, that's good. So we can do the same thing for ridge. Let's copy this. Wait, let's go search. Okay. Let's take from here. Okay, for ridge, let's use the same alpha. Let's add another parameter here, solver. Solver. Let's choose between stochastic, clinical, and least square. Then we've got ridge already, right? Yeah, we have ridge here. So let's ridge our estimator. Let's change the name here. Let's make this ridge CV. Okay. So ridge CV is good set on ridge. Param grade CV is 5. Negative mean squared error. N jobs -1. Good. And let's call this ridge CV. Dot fit on next train scaled and that should be good. Okay. That is done training. You can see the best I'm going to show the parameters. Yeah, okay. Shows you the param grid. Shows you the things that it actually works with here. Values of alpha, and it should show the value, the solvent that it works with. And then the estimator. Okay, let's do the same thing that we did here. Let us see if this would be better. Let's call this negative ridge CV. And let's call this ridge CV. Right? And let's put them both. Okay, so we have something similar, another 2.8 something, let's see. 2.84906. Okay, this is slightly smaller than that one, which is slightly better than last one. Well, so our best MSC is actually containing the best right now. And then these are our parameters. You use the stochastic, what is this? Something gradients, and our alpha is 0.306, some long number that I don't care to call all of them out. All right, so yes, you could answer with this, you could answer with this, and you would actually meet the criteria. Let's take it a step further. Since what we did for the previous week was tree-based models, right? So let us try trees. Yeah, so someone asked that question about models that don't require scaling or don't depend on the scale of the data. This is one of them. Decision tree. Decision trees do not depend on, they don't require scaling. So if you don't scale, you'll be good. Okay, so let's import that. I don't think we have scaling the tree. Let's import decision tree person. And let's create an instance. Let's say reg is let's give the random states. Let's try the base model and see what we get. Reg that fits. Extreme scaled Y train. Then we have Y pred. Let's go to Y pred reg. Now the base dot predicts on X test scaled. Okay, so let's just see what the MSE is. I don't like doing this in blocks, my view. I'm good. Should be 2.2. Guys, I think we have a new winner. It's all the way down to 2.2. Okay. Let's try a combination. Let's try an ensemble. Let's try lots and lots of decision trees. Right? Yeah. Ones that fits. X train field and Y train. And then let's call Y pred forest. As forest to predict. As an X test scale person. Yeah, that looks good. And let's print the MSE. Two 2.01, a new winner. It gets better and better. Amazing stuff. And these are the base models. So this is without tweaking. So far our best base model is forests. I guess we should just tweak forests for one final, run around and then see if that is better than everything. So let's have a param distributions. This one will tweak 3 things. Let's do an estimators. If there's any of these parameters, if there's anyone that you don't understand, please ask and I will try to explain them, okay? Any of the parameters in our distribution list, in our parameter distribution. So you know exactly the things that we are iterating over. You can't have flux as our number of estimators, so then let's do max features. Auto and squares. And max depth. Oh, by the way, we all understand the concept of decision trees and random forests, right? Does everybody understand? Please unmute your mic and respond. I can't see reactions if you are reacting.
I understand.
All right, cool. Does anybody not understand? Okay, I think that's enough. That's all we need. This time around, let's use random seeding. So it don't take so much time because we have a bunch of features now. And a bunch of trees. Let's come out this way. So estimator is forest. Param distributions is param distributions. Number of iterations. So instead of going through every possible combination, every possible combination of parameters, we're just going to do 10 random combinations. Then do threefold cross validation instead of 5 this time. So it's fast. Let's put our scoring same neg mean squared error. Then random state. Let's make it 9 as per usual. And then number of jobs. Let's make that -1. So this is every single processor. Okay, so let's call rf random. Rf random.fits on x train scaled. Excuse me. And y train. Then let's call let's just leave this in this cell. Fits. Make sure there's no error. Okay, looks like that's fine. Then let's call widespread RF. That would be RF and let's predict. Predicting. Okay. Unsuccessfully. We're predicting on X test scale. Right. Or let's just do this. What is that thing? Yes, yes, yes. So best MSC would be negative RF random, or rather we hope that would be best MSC. RF random, the best score. Then this is going to be RF best estimator, right? Okay, fingers crossed. What do we have here? 2.0509. Let's see the last one. 2.01. Ooh. So our base model is that. So our base model is actually better than what the random CV gave us. That's a better MSC. It's 2.05 and this is 2.01. So that means that when the random CV takes its 10 iterations, the base model was not part of the 10 iterations or anything better than the base model. This was the best out of the 10 that it picked. Well, this will still serve for our answers. You could still submit this as a best MSC or best model, or you could come back here and, use this for your best MSC and best model. Right? Just you just have to set best MSC. Best MSC would be equal to forest MSC. So you just copy this in there, and then best model would be forest. Right? And that would be your response for that. Yeah, so I think we've played around with a couple of models, seen how the MSCs have been dancing up and down. And oh yeah, there was something else I wanted to mention. For this data set, there are not a lot of features, right? But at the same time, we saw that we had amount and amount 2, we had length and length 2, and rental rate and rental rate 2, right? So, you might be tempted to just drop one of them and be left with the other, since it seems like a duplication. It's best to not assume. Don't assume it's a duplication. Check. Investigate. When we did the describe, we began to see that they were not the same. They might still be very similar and, have a strong correlation, but we do know that they're not the same. So we have amounts, and then there's amounts, right? Yes. So this is the minimum here is 99 cents. The max is 11.99. And like we saw before, the mean here is 98 cents, max is 143. And the mean is 23.355. The mean is 4.21. So I already know that's not the same. So if you're considering whether or not to go ahead with using them, you can check their correlation, right? You can check the correlation amongst them. You can plot the pair plots. You can plot the seaborn pair plots as well to see if they are perfectly correlated, or is it 31? And you can do those things to decide if they actually have that strong a correlation for you to want to drop some of them. And then if they do, I would also advise to take it a step further and check how much variance is described by each of those features, so that you can drop the features that have less variance and go with those that have more, that have that describe more of the data basically. So yes, I think that brings us to the end of the project run through. If you have any questions, now would be the time to ask. Let me get the attendance sheet. Any questions? Any contributions? Any feedback?
Yeah. Hello, sir.
Yes, go ahead. I can hear you.
Yeah, I just want to confirm. So if let's say two features have have strong correlation with each other, so and then we also check the variance and if you take the like how much they explain each other, so we can. So are we going to drop the like going to drop one and then use the other one, or like how does it work?
Yes, so if you have a correlation of 1, that is a strong positive correlation, or negative 1, which is also a strong negative, you can drop. It means that those two features are giving you the exact same information. And I gave an example during one of our classes: weight in kilograms and weight in pounds. Correlation 1, because as weight is increasing in kg, it's increasing by practically the same ratio in pounds, right? So if you have a data set that contains weight in those two metrics, you can drop one of them. Let's say you have height in centimeters and height in meters. Correlation is 1, because they are basically the same scale, giving you the same information. The difference is just in the position of a decimal point. So you can decide to drop um, the one in cm or drop the one in meters. In these two cases that I've called, the variance will most likely be the same or very similar. So it may not matter which you drop and which you don't. But for something like this, like the amount and amount 1, we're already seeing some sort of difference in spread. So the correlation might not be 1, right? It may have like a high correlation, like 0.9 or 0.8 something or 0.9 something. So in that case, it's not exactly, the mapping is not exactly 1:1. Now, in the case where you have a lot of features, or you're trying to reduce how many features you're working with, reduce your dimensionality, or you're not impressed with the model's performance and you want to see if the dimensions are affecting it, then you can go ahead and check which has more variance, which has more spread. Then you drop the one with lower variance, because that means it contains less information. It gives your model less to make its calculations and inferences on. The one with the wider spread will be better to work with, because it's it's spread wider across the graph, and you can see the difference between one data point and the next data point. They're not clustered so much together. Does that answer your question?
Yes, thank you.
All right. Thank you for that question. Okay, short and Chima. I will drop it in the, I'll drop the notebook in the Chima. Have you done your project? Have you finished your project, Chima? Before I come and give you expo. I'm looking for attendance. Where is it? Okay, this is it. I hope this link is complete. So I'll drop the notebook in the Discord channel. And the attendance is in the chat. Please go ahead and fill the attendance. If you have any questions, contributions, feedback, please go ahead and mute your mic and speak. And in the absence of any questions, once you're done with the attendance, you can go ahead and drop off. Thank you guys for joining the breakout session today. I hope it was helpful and you're able to pick one thing or the other, or get some clarification on one thing or the other. And yeah, if you don't, you can just drop off, and I'll see you guys on Discord and probably on the next breakout session. Hopefully we have a better turnout than this. This is saddening. Again, close to tears. If you see any of our course mates, if you see any AIML cohort 2 member outside on WhatsApp, on LinkedIn, on Discord, let them know the damage that they caused today. They brought me to tears, and it was an ugly sight. Okay, guys, good night or good morning, depending on your time zone, and have a wonderful week ahead.